Today we will be talking about function analysis. This is the first day of function analysis, and I always begin with a discussion on the basics of reading a graph. First of all, when we look at a graph in calculus, we always read the graph from left to right. Always from left to right, just like you read a sentence in a book. When I ask, does the function go from positive to negative, I'm asking, as x goes from the left to the right, does the y value change from positive to negative? So we always go from the left to the right. Okay. Another thing to make note of is that we only consider the domain of the given function. When we are given a function, it is assumed to be true for whatever values make it defined. That's its domain. And this is something that we don't usually kind of focus on. It's just always in the background. So if, for instance, if I were to tell you the original function was y is equal to natural log of x, well, the domain of that function is 0 to infinity, not including the 0. So any result that we have would be on that domain that we started with. We wouldn't end with a domain that we didn't start with. Okay. Another thing is that the graph is assumed to continue forever in both directions. You will not see arrows on the ends of graphs. All right? It's assumed that they go on forever in the direction on which they were going when we stopped drawing it. So right here, this is assumed to keep going forever and ever in that general direction. This is assumed to keep going in that general direction. Okay? Now, if I wanted it to stop, I would put a little point there. And then if you see a little point there, that means yes, it is only good right there, and it stops. You cannot make any assumption on outside of that if you see points at the end of it. Alrighty, let's talk about increasing and decreasing intervals visually. So just by looking at the graph, what does increasing and decreasing mean? So as x moves from left to right, so as x moves to the right, if the function is going up, if the curve is going up, if the y values are increasing, then the function is said to be increasing. As x moves to the right, if the function is going down, the function is said to be decreasing. All right, and I'm going to have you in class highlight this graph in, what color do I have handy? Well, I have purple here. In purple, where the function is increasing. Okay, so I'll have you guys get out something to highlight your graph. Whatever color you have, you can call that increasing. So this function is increasing right here. It's increasing right here. It's increasing here. And it's increasing here. And is increasing here, and then it continues to increase forever according to this graph. All right, I'm going to grab another little highlighter here. I have orange, so let's highlight the above graph in orange, where the function is decreasing. So we are decreasing here, we're decreasing here, 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 and here. That's decreasing. Okay? Visually. And we will discuss when we talk about decreasing exactly and increasing exactly what it means to be at one of these points right here. So at all of these little points. What does that mean? We'll discuss that when we go from just discussing it visually to the actual definition of increasing and decreasing. In this little intro, I just want you to get an idea of what it looks like to be increasing and decreasing. All right, relative extrema visually. There is an interval or a neighborhood around the point A, f of A, that's this point, at which f of A is the largest value of f. That makes f have a relative maximum value of, it's the y value, it's f of A. That's the y coordinate there. So it has a relative maximum of f of A at x equals A. Another phrase that we often see for relative maximum is local maximum. They are interchangeable. Relative and local, interchangeable. Okay? There is an interval around B, f of B. Here's B, f of B, at which f of B is the smallest value of f. Do you see the interval? Do you see an interval where it's the smallest? We could take that interval right there. We could take that interval right here. We could take a lot of intervals, actually, where that is the smallest value of f. That makes f a relative minimum. And the value is f of b, and it occurs when x is b. Another phrase often seen for this is local minimum. Okay? Is the point C, f of c a relative minimum according to this definition? So here's C, f of c. Is this the lowest value of y of f in some neighborhood or in some interval? Yes, it is. It's the lowest value of f in that interval, isn't it? So yes, this is considered a relative minimum. Yes, it is. Can a corner or a cusp be a relative or local maximum or minimum? Yes, absolutely. And little terminology, relative extrema are either relative maxima or relative minima. Extrema is the plural of extremum. Maxima is the plural of maximum, and minima is the plural of minimum. Okay, so that's our little brief intro to function analysis.